Welcome to a video on Chapter 4, Section 1, more about relationships in two variables or bivariate data. But instead of it being linear this time, it's either going to be exponential or power. The difference between linear growth and exponential growth is that linear growth increases by a fixed amount. It's an additive process, whereas exponential growth increases by a fixed percent or a multiplicative approach. There are two types of transformations we're going to look at in this chapter. They're done the same way in the calculator. It's just what data do you use to do the analysis. One is exponential and one is power. So exponential is when the variable is in the exponent, and if you can't read the function there, this is f of x equals 2 to the x. So the variable is in the exponent, that's why it's exponential. And in a power model, it's the variable that's raised to a power. So for example, your basic just parabola, x squared, that's a power model. And what we're going to do with data is if it's an exponential model, we use our x values, but then we run a regression using the log of the y values. And if it's power, we're going to run a linear regression using log of x, log of y. So it's very similar. It's just one versus the other. Now, the question becomes, what if I forget which one's which? How can I figure out quickly whether it's x log y or log x log y? So if you go back to your algebra and log skills, if we have y equals, let's say 2 to the x, if I take the log of both sides, what a log does is it takes this exponent and moves it in front. So I get log y equals x log 2. So you notice only the y is in the log. So for our exponential, we just get x log y. Those are the two terms we're going to be using. Now if we do power, and if I had y equals, let's just again take x squared this time. If I do log on both sides, the 2 comes out front, but the x is within the logarithmic function. So this is why a power model for our data uses log of both x and y. So that's a quick way if you're not sure whether you have to do x log y if you're using exponential or if it's log log. You can just do a quick log, pick a random y equals 2 to the x, and you can do the log of both sides and then see that the variable comes out front for exponential. All right, now when do we use one versus the other? In some of these book examples and practice examples, you may not know the science behind them, and so you'll have to just look at their R values when we go to run regressions and say which one is stronger, so I'll use which model you should use. However, in the real world, if you're running analysis, hopefully you know the situation, how it's modeled in the real world. So is the thing you're measuring exponential or power? Hopefully you know from the application. For example, if it's biological, generally it's exponential, like bacteria growth, investment, that's all exponential. Power models tend more to be with the empirical formulas, like from physics or math, when you do like volume or surface area, force, velocity. So those are some examples of the differences. And generally the things used in statistics end up being the exponential model because that has more interest in science and studying statistics. All right, so here's one example. We have Moore's law, which was started in 1965 to predict the number of transistors in an integrated circuit chip. Now, a circuit chip, the chips on your computer, on the board inside your computer, have a bunch of these little tiny transistors inside each chip, and by a bunch I mean thousands. Um, and they help move the signal around, figure out the logic, do all the fancy things computers do. So it was hypothesized that it would double every 18 months, and this became Moore's law because Gordon Moore was the one who uh, stated this hypothesis. So here are the actual processors up through 2010 and how many transistors were in them, and then a nice little graph. So notice also the y-axis is years since 1970. So you also have to be careful if you were trying to run an analysis on this that you have the right numbers in there. Otherwise, the equations come out looking different. All right, so this is in fact exponential because he thought it would double every every 18 months. So if you're doubling, that's where your formula is going to be 2 to some power. And the reason we're going to want to make our data linear is then we can run a linear regression. And in the previous section, we talked about R and R squared. And these really only have a practical meaning when we're talking about linear regression. So these can tell us a lot about strength and how much our model helps predict the response variable. So they're very helpful in our analysis. Therefore, if we can, we want to make things into linear regression. So this one, since it's exponential, we're just going to do x log of y. Now you'll see it says lny. If you don't remember, that is log base e, and e is approximately 2.71, and it's like pi goes on forever. For those taking calculus, you are going to start to be very much dependent on natural log in terms of you're going to like it a lot more than log base 10. It's because it's used a lot more. You can, in any of these situations, use log base 10 or natural log. Your equations will look a little different, but in the end, you'll get the final answer the same if you're trying to predict a value. So either is fine, you just have to state which one you're using. And this plot now is, you will see the natural log of transistors and the years since 1970. So the x value is the same, but the y-axis has changed. And this looks very linear now. We're not going to bother typing these in. I have a computer output for this one. And this constant, that will be your b or y-intercept. On a computer output, almost all computer outputs have a similar setup for linear regression. And then the one that has the words of what is being measured, that is your slope line. So this number here, that is your slope, and that is your y-intercept. Now the other ones, the p, the t, the standard error, we're not going to worry about that till later in the course. And in AP statistics, we don't do the R squared adjusted. That's for smaller samples. It's just not in our curriculum. We just use this as our R squared if we cared about what the R squared value was at this point. It's very strong. So in my equation here for the line, you want to make sure you put in the whatever log you're using of the y equals the y-intercept plus the slope times the x value. Now, notice this is done using words. You could also do natural log y hat equals 7.0647 plus 0.36583x. And that is fine as long as you define what y hat and x are. So y hat would be the predicted number of transistors. And x is years since 1970. All right, so let's actually answer the question that's asked here now. How many transistors would the Moore model predict to be in the i9 chip that is being produced this year? Well, this was last year, 2019. All right, so I am going to erase this, and we'll just use X and Y right now to make it easier. So we have natural log of y hat, 7.0647. And since this is years since 1970, that will be 49 years. So X will be 49. And if I substitute this in, I get 24.9940, 24.9907. Now that is not the predicted number of transistors, because first of all, if we were to go back to this, that's only 24 transistors can't be. This is the natural log. So we have to do the inverse function, which would be raising e to this power. So this would be e to the 24.9907, which comes out to be about 7.13 times 10 to the 10th transistors. Now I looked up, and Intel doesn't give their actual transistor count, but it's hypothesized by some people that the i9 chip did have about 7 billion transistors, which is 7 with 9 zeros after it. So it's a factor of 10 less. And my question to you would be, why is our prediction not, why is it a factor of 10 away from the actual? So think about that for a second and then come back to the video. So if you remember in chapter 3, extrapolation is something you want to be careful of. And our data set only goes to 2010. So this pattern may not continue. And in fact, it possibly could be impossible for this to continue because there might be a limit to the number of transistors that can go into a chip. So we were extrapolating our data because 2019 is outside of the data set that we have. So the exponential model may not continue to be true. And that could be one reason the calculation is off. The other reason it could be when you start to do exponentials, small changes can make huge differences in when you go to this step, because if you're raising something to a power, just a small change can change the answer by quite a bit. All right, so let's do one more problem. And this time we have to decide, is it power or exponential? So we have the depth we are in a lake, and then how intense is the light in lumens as you go deeper and deeper into a lake. All right. So one way you can tell if it's exponential or power is that if it has a constant ratio, then it is exponential. If it just has some random, if it changes, then it's power or something else. So to get the ratio, I can do the 168 divided by 120.42 and then keep doing that down the road. The problem with this sometimes is if your x's aren't consecutive, then the ratios won't be consecutive, and it can get a little more complicated to check the ratio. It's still doable, but it takes a little more thought than just dividing each consecutive one by the other. If you do this for each of the terms, you get 1.4 each time. So we know that this is exponential. And if you were to do that for each pair, you get 1.4. I'm going to show you though how to check if you have no idea of the basis of the information and you can't just check consecutive terms for a ratio. So what you want to do is take out your calculator and type in these values and then unpause and we'll go over the calculator method of this. All right. So here in my calculator, I have entered into my list, the two lists. And now if I want to do log, because I don't know if I want log of both or log of one, so I'm just going to do log of each list. Let's do log base 10. So I'm just going to do log and then second and 1 to get list 1. You don't have to close parentheses on this. You can just press enter and it'll do all the logs for you. And then here I'm going to do log of L2. It can be useful to write down what each list represents because it is very easy to forget which list is what log and make the wrong pairs. All right. So next, we are going to just graph to look at the data, make sure it's actually one of these two. It's not some weird look. So if you go to your scatter plot, we go to list 1, scatter plot's the first one, and we got our lists right. So if I go to graph, as normal, my zoom is messed up, so I go to zoom stat. And there's definitely a decay going on there, some kind of exponential or power. They can look the same. All right, so what we're going to do is go to stat calc and run a linear regression. So let's first do x and log y. So that'd be L1 versus L4. And then you can just jot these numbers off to the side. So it's the R value is negative because it's would be a negative slope, and it is 8 nines there if you are writing this down. Then we can try this again, but this time with L3 and L4. And you will notice the R value is much less, meaning it doesn't fit as well. I mean, it's still really high, but the exponential model is better, and this case is exponential by its nature for the science involved. All right, so then we can write down our equation. Let's do that slideshow from current slide. So our equation then is log y hat equals negative 0.1446 plus 2.9484. Oops, where's my x? My x is with that number. Y hat is the predicted. Light intensity. And x is depth. And it doesn't hurt to put the units here, meters, lumens. Let me give you one final question, and that is, what would be the light intensity at a depth of 8.5 meters? First thing you want to do is look, would that be extrapolation? It is not, because it's within this data set. It's in between 8 and 9. So we also know if we do our problem right, it should be between 62-ish and 44. All right, so I'm going to substitute this in. And you can do this along with me. I'm going to just type this into my calculator. All right, and we get log y hat equals 1.7193. So to get y hat, since this is base 10, I have to do 10 to the 1.7193. And we get 52, we'll say 0.4 lumen. Oh, everything's to the hundredths. Let's do it to the hundredths. Well, it does round to 4 lumens. And that falls within the expected answer, so we are good. Now, we're not going to do a lot with exponential and power, but it is a very useful tool to change things to a linear regression, and then you can do everything you learned in chapter 3. I hope this was helpful, and I'll see you in the next video.